topic is plant electrotropism. The purpose of the presentation: make an argument for another plant tropism in addition to phototropism and geotropism, and to give a glimpse into the hidden natural electric world all around us. What is plant electrotropism? It's plant geometry influenced by electric forces for this presentation. There's also magnetic forces here, but beyond the scope of this presentation. There are 4 presentation parts. 1 is electric field lines of force. 2 is voltage recordings. 3 is electric forces. And 4 is electron source. Part 1, electric field lines of force. Before I can speak about electric field lines of force, I need to speak about voltage circles. And it's a procedure. I was working with an electrical engineer in 1999. I asked him for a procedure for tracking electricity in the ground. He gave me the voltage circle procedure. You orientate yourself to north, south, east, west. Find the center point of a circle, typically 50 feet in diameter. Install a ground rod at the center with a wire hooked to it, a voltmeter in between, another ground rod. Then you proceed to take readings around the circle. In this case, it was millivolts AC. And that allowed me to draw what was called an equipotential line from the lowest voltage on one side through the center point to the lowest voltage on the other side. And perpendicular to that is the electric field line of force, starting at the highest voltage of the circle, going through the center point and to the highest voltage on the other side of the circle. And that's the electric field line of force within that circle. And the arrow indicates the direction. With this procedure, I was able to do electric survey, and I show you a portion of that here. You can see the voltage circles. This area is about 500 foot by 700 foot, and it's a hay field. And you can see the resultant electric field lines of force. The electric field lines of force rules learned. 1, they affect each other. They curve and flow around other electric fields. They change direction because of other electric forces. Different soil types had no noticeable effect on their direction. They flow straight in the absence of other electrical forces. They flow straight through electrical forces equal on both sides. They're a tool to help visualize electricity in an electric field continuum. And they gave me the idea that plants follow the same rules. When I first understood that these lines were affecting each other, I asked myself the question, what else in nature displays these rules? And plants just came to mind. It's not like I chose this subject, it chose me. Here's a picture on the right of a maple tree branches that are following the electric field lines of force rules. This is basically a line charge, which is in the trunk. For 16 years, my electrotropism learning process was largely trial and error. But the observation of the thousands of plants following these simple electric field lines of force rules has inspired me. Here's a picture of some palm trees I found about 10 years ago in a magazine. There's several feet between each trunk at the base. When the plants were small, if there was an electric force between them, it was likely small. As the palm trees grew, the electric force between the trunks would have increased, and the heads. The electric repulsive force between the trunks and heads would cause the trunks to lean away from each other. Only electrotropism can explain this plant-to-plant behavior. I don't believe there's a shortage of sunlight here, and I don't believe geotropism can explain plant-to-plant behavior that's going on here. It's possible beneath the sand these plants are hooked together, you can't see it, but I don't know that. So you're familiar with the Lichtenberg figure. It's a charged block of plastic, and it's quickly discharged, and it ends up showing electric field lines of force. It's a physical record of electric flow. Plants which are easy to see electric field lines of force, young maple trees without leaves, upper tree branches, weeds such as lamb's quarter, palm tree trunks. Veins on leaves are electric field lines of force. Blue spruce needles are electric field lines of force. Plants which are difficult to see electric field lines of force. Leafy plants dominated by phototropism, older woody plants with many knots, lower tree branches, non-woody plants which droop because of gravity, woody plants with physical or disease damage. Gravity, wind, snow, ice, etc. all cause physical damage. Part 2, voltage recordings. The plants below listed here are not shown in this presentation. Here's the equipment I used, a laptop, a PC-based oscilloscope, 100-foot coaxial cables so I could take readings on trees and have the laptop and oscilloscope in the shop where they're out of the weather. The voltmeter, some various wires. Not shown here are the ground rods, conductive paste, and some special clamps that I made. Here's a typical voltage recording schematic. It's based on the Tektronix A-B application note, which is designed for any oscilloscope, in particular this oscilloscope, because it's not isolated channels, which means that the reference or negative leads are one wire. So really it's just 3 wires coming out of 2 channels total. Typically the clips were hooked to the end of the branch or 18 inches down the branch or the trunk of the tree, and those would be the positive leads on the oscilloscope. There's a ground rod, which is usually 7 feet away from the tree. The laptop, I always operated on battery power, so there wouldn't be any harmonics interference. And I also shut off all the equipment in the shop to make sure that wasn't interfering. Here's a picture of a large poplar or aspen tree. On the lower left, you can see the ground rod circled. The positive channel 1 lead was hooked to the branch tip up on the upper left, and channel 2 positive lead was hooked to the trunk, to an eyelet that had been there many years. Here's the voltage recording between the tip and the trunk. The vertical axis is volts per division. Horizontal axis is time for division, 5 seconds in this case. The red line, as you're called, channel 2, is in the trunk, and it's 0.85 volts DC. And the blue line is channel 1 at the tip of the branch is 0.18 volts DC. And they're both negative. But the voltage in the trunk is considerably higher than at the branch tip. Here's another recording of the voltages, but channel 1 is still at the branch tip, and channel 2 is 18 inches along the branch. You can see the channel 1 is in blue, 30 millivolts for division. Channel 2 is red, same volts for division. The reference lead is the top axis. So again, it's negative voltages. And the difference is 90 millivolts, and I use that 90 millivolts in later calculations. I also measured this particular branch for ohms resistance and got 2 mega ohms average. And there's no leaves yet. It's 45 degrees temperature. Here's a similar setup for a sugar maple tree. Ground rod several feet away. Looks like the red lines have shifted. The channel 2 positive lead was at the trunk, and the channel 1 positive lead was at a branch tip, similar to the last reading. But this tree is in Connecticut, the previous tree was in Michigan, so they're 900 miles apart. So again, the voltage at the tip to the ground rod is minus 80 millivolts, and the trunk voltage to the ground rod is minus 650 millivolts, so 570 millivolts difference. Now, I assume that the negative voltage is the same as you would see if you took a battery and a voltmeter and you took the positive lead of the voltmeter and you measured the negative lead of the battery, and vice versa, you'd get a negative voltage reading. And since the positive lead is at the negative end of the battery where the excess of electrons is, I'm saying that this negative voltage readings here are also showing excess electrons. Discussion of recordings. Only live branches showed significant voltage. The test leads in the air on the ground showed little voltage. It's best to use conductive paste on the clips. It's best to use stainless steel screws in the large branches and trunk. The voltage recordings are repeatable. The recorded voltage can be checked with a digital voltmeter. Negative charge equals excess of electrons. Positive charge equals deficit of electrons. Electrons seem to flow up the tree and outwards to the branch tips. Part 3, electric forces. Electric force equations, calculations, resultant vector force. Electric force equations in Ohm's law. Electric field strength equals force divided by test charge. Coulomb's electric force law and Ohm's law. So what I did was set up a example 2D vector force system at the branch tip. And this, as Dr. Scott noted, is what engineers like to do. This is leading to a model. And it's probably about the most important part of this presentation because it shows that there's enough force here to make things happen. So I use what's called the method of sections at the tip, and that's where you do an imaginary cut across the tip and then you apply forces to the tip to bring it into equilibrium. That's an engineering trick that engineers use. What I didn't do here was show a shear force and bending moment, just to keep it simple. So there's only axial forces shown here. For F1 is the Coulomb force between the charge in the tip and the charge in the earth. Now the charge in the tip is what I had calculated from remember that 90 millivolts at the branch tip of the aspen tree and 2 mega ohms of resistance? So that gave an amperage. And what I did is that's coulombs per second. I multiplied by it by 1 second. And I got coulombs. And since charge tends to accumulate at points or branch tips, I multiplied it by 10. F2 is the Coulomb force, which is the charge in the tip between the charge in the trunk, and I assumed the charge in the tree trunk was 100 times the charge in the tip. F3 is the coolant force between the charge and the tip or the branch above. F4 is the coolant force inside the tip. And F5 is the electric field force between the charge and the tip and the electric field around the branch. And W equals tip weight. Please note all angles are assumed. And there's actually an error on F5 on the diagram on the left. It says F5 equals tip to earth E field, and it should say branch E field. What is the resultant vector force R? After 2 pages of calculations, and I've got them in the back there if anybody wants to read them, we get the resultant vector force at the branch tip. W is 0.0049 newtons. F1, the charge in the earth, is 0.000052 newtons. The force pushing horizontally to the left between the trunk and the tip is 0.24 newtons. And the coolant force in the branch above is 0.3 newtons. They're getting bigger. And the force inside the tip is 2.4 newtons. Much bigger. The F5 is the electric field force between the tip and the branch, and it's 0.00072 newtons. And you can see the resultant force is 2.7 newtons at 21 degrees, and the original angles were assumed 30 degrees, so it dropped. And then there's an equal and opposite force on the other side holding the thing onto the branch. So that gives a resultant vertical force of approximately 197 times the weight of the tip pushing up. But you can see that depends on the angles I assumed. You could easily see that if I had assumed a flatter angle on the starting out with, that the resultant force could actually end up pointing down. Or if I'd taken a branch in the middle of the tree where there's equal forces on each side of it, the resultant force could easily be angling up, farther up. Or taken to the apex of the tree, you can easily see that all those forces would be pushing directly upwards, except for the weight. And this model seems to fit pretty closely what's happening in real plants, real trees. The other important thing to note here is that the force within the tip, the 2.4 newtons, that's about 0.6 pounds. That's probably directly involved with the tip growth, elongation. It's a fairly good sized force. And the branch forces around it and the weight, all the electric forces around it, are directing its direction. They're changing its direction. So here's a tree electron flow drawing. It's not a voltage drawing. It's based on electron flow notation, not conventional flow notation. And that means where there's an excess of electrons, it moves to an area of less electrons. That's the direction of the flow. The tree electric field lines of force, shown in magenta, are interacting with the earth electric field lines of force, shown in blue. And a question comes to mind: why are the electrons being attracted to plants? And I'll try to answer that near the end of the presentation. And I put all my positive charges up near the top of the drawing. Dr. Pollock might not agree with that, but I didn't know any better, and that's where they're at. So here's a diagram from the University of Bristol School of Biological Sciences, plant voltage diagram, 2013 bee research. Many of you probably remember seeing this a couple years ago online. The Diagram on the left is electric potential, and you can see the equipotential lines. And you can't see the earth voltage here, but the plant voltage seems similar to the earth voltage on this scale. And that fits with what my recordings were. Most of my voltages were less than 1 volt. And on the other side, you can see the concentrated charge at the tips. So how many electrons are flowing to the Aspen branch tip per second? Using Ohm's law, V equals 90 millivolts and R equals 2 megaohms, we get an amperage calculation of 4.8 times 10 to the minus 8 amps, or coulombs per second. An elementary charge is 1.6 times 10 to the minus 19 coulombs. And by definition, 1 electron equals 1 elementary charge. Therefore, the number of electrons per second equals 2.8 times 10 to 11 electrons per second are flowing towards the end of the Aspen branch tip every second, and likely all the other Aspen branch tips. It's a lot of electrons. Where are all electrons coming from? Where are they all going? Part 4, electron source. The left picture is a Faraday cage test chamber I built. It's 4 feet high, 3 feet wide, 2 feet deep. It's also a humidity control chamber and a temperature control chamber. You can see in there the laptop is sitting in there, and beneath it there's the oscilloscope, and there's a plastic tub in there with it. And inside that plastic tub, on the picture on the right, there's a corn sprout. It's wired into the oscilloscope, and it's on a pivot. The reference lead is a wire, very fine aluminum wire wrapped around the root, and then some conductive tape squeezed around it. That's the connection at the other spots too. Channel 1 was hooked a little farther down the root. Channel 2 was hooked on the stem. The reason it's not hooked farther up the stem is because this sprout's got some age to it, and it grew through, it didn't go with it. They were wired when the sprout was quite small. So, and then there's a pivot shaft. And the pivot shaft allows me to rotate the corn sprout. So here's a recording of that test setup. It was done in August 2013. When the root was touching the water, I put water in the bottom of the tub, and then when I rotated the root down to the water, the electrons in the stem increased. The time per division here is 50 seconds, so it's almost 3 or 4 minutes that the root was touching water, and there was a steady voltage. That implies amperage flow. And then when I rotated the root into the air, it took about 10 seconds for the electrons to leave the stem. I don't know where they were going. There's wires hooked to this thing, so it's not natural. It could have been bleeding back through the oscilloscope, which is only about 1 megaohm of resistance or impedance. Or they could just been leaving the plant. The significance of this diagram is it shows that the electrons are coming from outside the plant. They're coming from or through the water to the root and moving up to the stem. Here's a picture of a cherry tree outside my house. I installed 16 number 8 2.5-inch stainless steel screws, and I put a label on them so I could take voltage readings. My wife wasn't happy. tree's fine, it's doing well. And you can see the bird feeder does not have an M on it. So the first thing I did was I measured a root voltage in reference to a ground rod several feet away, and I got a strongly negative reading. It was less than a volt, but it was fairly high. And I checked that with a couple other trees in the area too, and all three of the roots I checked were negative. The trunk, however, was slightly positive. Branch 4 was negative. Branch 3 was negative. Branch 2 was negative. An offshoot of branch 2 was slightly positive. Branch 1 was negative. Offshoot of branch 1 was slightly positive. And the rest of the readings were negative, strongly negative. So, what's going on here? The two branches that are offshoot branches are kind of buried inside the tree. So it's possible that the electric field of the other branches around it are restricting the electrons on the outside of that branch. And maybe it's what's happening to the trunk too. Maybe this is not a tall tree, the trunk is short. Maybe the electric field above it is keeping electrons from being on the outside of the trunk. But it also gives a clue as to what is attracting electrons to the tree. When a tree respires or burns its sugar with glycolysis, there's a thing called a citric acid cycle that occurs. Now, acid, okay, that implies hydrogen ions. And if there's hydrogen ions traveling around the tree, that could be what's attracting the electrons to the tree. Conclusion, part 1, electric field lines of force. Woody plants display electric field lines of force. Conclusion, part 2, voltage recordings. Plant voltage readings can be done with a digital voltmeter or oscilloscope. Conclusion, part 3, electric forces. The resultant electric force at the branch tip directs tip growth direction, in my opinion. The electrically directed growing branch tip creates electric field lines of force branches. As the tip grows and the direction changes, the lignin forms behind it and it forms an electric field line of force. Billions of electrons are flowing towards the end of the branch tip each second. Conclusion, part 4, electron source. The corn touching the water showed electrons are coming from outside the plants and traveling upwards in the plants. The cherry tree shows both positive and negative voltages. Are the positive voltages within the plant attracting electrons? Here on the left is a Lichtenberg figure, which is a physical record of electrical flow. On the right, you see a maple tree. And from what you've just seen, the electric field lines of force, the voltages, the forces, I think it's a physical record of electrical flow also. Thank you.